In this video, let me consider one example on initial conditions and transient analysis. The switch S is changed from position 1 to 2 at t equal to 0. Steady state conditions have been reached in position 1. Find the value of I, di by dt and d square I by dt square at t equal to 0 plus for the circuit shown below. This is the given circuit. Here S is the switch. So switch is connected to position 1. So during position 1 it has reached the steady state. It is said that steady state condition have been reached in position 1. It means that when the switch is connected to position 1, that is connected to here, the circuit has been reached the steady state. So we know that in steady state, inductor acts like short circuit and capacitor acts like open circuit. Now let me redraw the circuit considering the steady state, and the time at steady state is represented at t equal to 0 minus. So now let me redraw the circuit for t equal to 0 minus. So this is the circuit when the switch is connected to position 1 and the circuit was in steady state. As I shown here, the inductor acts like short circuit, so I have removed inductor by short circuit, and there was a capacitor, I have removed it by open circuit. Now the current flowing in the circuit is represented as I of 0 minus, because at t equal to 0 minus the switch is connected to position 1. So now let me find I of 0 minus, that is I of 0 minus is equal to 20 divided by 10 is equal to 2 amp. So this is the current flows in the circuit before the switching operation. So now also we know that I of 0 plus is also equal to 2 amp, that is nothing but I of 0 minus. That is current in the circuit or current through the inductor immediately after switching operation is same as before switching operation. So now it is said that at t equal to 0, the position will change from 1 to 2. So let me redraw the circuit when for t greater than or equal to 0. That is for t greater than 0 plus, the circuit is shown below. So this is the circuit when switch is connected from position 1 to position 2. So first let me apply KVL to this circuit. So there is no any voltage sources. We can say 0 is equal to, also we'll assume that the capacitor in the circuit, at the beginning the capacitor is uncharged, therefore we can write Vc of 0 minus is equal to 0, or it is same as Vc of 0 plus. So now let me apply KVL to this circuit. That is 0 is equal to voltage across resistor is Ri of t plus voltage across inductor is L di of t by dt plus voltage across capacitor is 1 over C integration of I of t dt. Or I can represent it as 0 is equal to R is 10 I of t plus L value is 1, that is di of t by dt plus C value is 1 microfarad, that is 1 upon 1 into 10 power minus 6 integration of I of t into dt. So now at t equal to 0 plus, I can represent equation 1 as 0 is equal to 10 into I of 0 plus plus di of 0 plus by dt plus we have 1 upon, so this is nothing but I can represent it as Vc of 0 plus, that is capacitor voltage across capacitor is Vc of 0 plus. So now we can see that I of 0 plus is 2 amps, so I can substitute those values. So I can write it as 0 is equal to 10 into 2 plus we have di of 0 plus by dt. It should be kept as it is, as we are finding first derivative of current, plus here we can see that Vc of 0 plus is equal to 0, because it is assumed that initially capacitor is uncharged, that is Vc of 0 minus was 0. So immediately after switching operation it will be same, that is Vc of 0 plus is 0. So this is 0. So therefore I can write it as di of 0 plus by dt is equal to minus 20 amps per second. I'll send this on other side. We'll get di of 0 plus by dt is equal to minus 20 amps per second. Now to get second derivative of current, I will differentiate this equation. I will call it as equation A. By differentiating equation A, we'll get second derivative of current, because already there is a first derivative in this expression. If we differentiate this, we'll get second derivative. That is differentiate equation A, we get, that is 0 is equal to R di of t by dt plus L d square I of t by dt square, plus integration and differentiation will get cancelled, will get I of t by c. So now at t equal to 0 plus, I can represent this expression as 0 is equal to R di of 0 plus by dt plus L d square I of 0 plus by dt square plus I 0 plus by c. So now let me substitute the values. I'll continue here. That is 0 is equal to R value is 10 into di of 0 plus. Di of 0 plus is minus 20. That is minus 20 plus L value is 1 into, we should keep this term as it is because we are finding that d square I of plus by dt square, plus we have I of 0 plus. I of 0 plus is already calculated, that is 2 amp. That is 2 divided by, and C value is 1 microfarad, that is 1 into 10 power minus 6. Let me simplify this. 0 is equal to, this is minus 200 plus d square I of 0 plus by dt square, plus we have 2 into 10 power 6. So therefore I can write d square I of 0 plus by dt square is equal to minus 2 into 10 power plus 6 plus 200. So simplifying this, I'll get d square I of 0 plus by dt square is equal to, we'll get minus 1.999 into 10 power 6 amps per second square. This is a second derivative of current. So now I can write the consolidated result as, we have I of 0 plus is equal to 2 amps, di of 0 plus by dt is equal to minus 20 amps per second, and d square I of 0 plus by dt square is equal to minus 1.99 into 10 power 6 amps per second square. Thank you for watching.